Okay, so this is our review. This is chapter 2. And I'm just waiting for my tablet to recognize things. There we go. So, we have a couple of rules that we have learned that we can apply. We have the power rule, which says that if f of x is x to the n, then f prime of x is n times x to the n minus 1, and that's good for every case except n does not equal 0. We also know that the derivative of the sine and cosine, I'm just going to let you look those up in the book. Make sure you include those on your cheat sheet, that we have all the trig functions. So, the derivative of the sine is the cosine. The derivative of the cosine is negative the sine. And there's other ones. What else do we know? We also know that if a function is something like this, then to take the derivative, we have to rewrite it as with a negative exponent. So we get it in the form that we can use it here. So anytime you see something like that. Likewise, if you have a square root or say a cube root of x, we have to rewrite that as x to the 1/3 power. So the square root is x to the 1/2 power, and the fourth is a fourth root. That's x to the 1/4 power. So that's how those work. So we've learned a few other things. We have the product rule, and you have quite a few examples of the product rule. And one thing you'll notice is that pretty much every problem on the test, if you have to use the product or quotient rule, I write it as h of x. That's true. Yeah, I think it's true for pretty much everything. So if h of x is the products of two functions, then the derivative is f prime of x times g of x plus g prime of x times f of x. And so when we have these kinds of problems, we write f of x is equal to whatever it is, and we do g of x, whichever what it is, and then you take the derivative of those functions, which you can either use one of these results. You may have to use the chain rule as part of that, but you get the derivatives of each part of the product, and then you plug it back into the product rule. And the same way with the quotient rule. So if h of x is f of x divided by g of x, then h prime of x is going to be f prime of x times g of x minus f of x times g prime of x, all divided by g of x quantity squared. So again, if you see something like this, then you need to identify the numerator as f of x and the denominator is g of x, and then list them, take the derivatives, then plug it into the formula. And, you should be able to do some simplifying, but you don't want to go crazy with the simplifying, or you can waste too much time. So those are the product and the quotient rules. Then you have the chain rule. And typically, if I'm just looking through my list here, if I call something f of x, it usually means that I'm expecting to use the chain rule. So let's just, in this case, we'll actually do an example. So let's say I have x squared plus the square root of x raised to the 3rd power. So what you do is you try to break that up into two parts. I'm not going to ask you to do any three-part chain rule, but you identify, well, you identify u of x, which is usually the term in the parenthesis, and then you rewrite the original function in terms of this variable u. So instead of x squared plus the square root of x, the whole thing cubed, you get u cubed. Then you take the derivative of this with respect to u, and you take the derivative of this with respect to x. Now, before I do that, I've got to rewrite this square root as x to the 1/2 power. So if I take the derivative of each term separately, as one of the rules says if you have a sum or difference of two functions, you can take the derivatives of them individually and just write out the results. So the derivative of x squared is 2x, 1/2 is 1/2 x to the minus 1/2. I'm just using the power rule. In this case, I would, if I have something to the 1/2 or to the negative 1/2 power, I rewrite those appropriately. So x to the negative 1/2 is 1 over x to the 1/2, and x to the 1/2 is the square root of x. So here I had to change it to x to the 1/2. Here I change it back. We only do this to make it so that we can use the power rule. So the chain rule says that if you have something that's a composite function like this, not a product, but a composite function, then the derivative is equal to f prime of u times u prime of x. F prime of u, I have up there, u prime of x. So then you have to get it finally in terms of in terms of x. So you go back up here, see what u was. U is x squared plus the square root of x. Make sure you put the power. You multiply by u prime of x, which doesn't change in this step because we're just trying to get everything in terms of x. And the question is, how much do I simplify this? Well, I would move this to the beginning, and I'd probably multiply by 3. So I would get 3 times 2x is 6x. 3 times that would be 3/2 times 1 over the square root of x. And all of that, notice I'm using parentheses to group these still together, multiplied by x squared plus the square root of x to the second power. So that's probably as far as I would go on that. Now you might have a case where it actually is a product rule and a chain rule within that. So for example, if I had x cubed times the sine of the quantity x cubed, I have a product which includes this term. So notice I used h of x again. So that's a product. So my first term would be x cubed. My second term in the product would be the sine of the quantity x cubed. So this one's simple because it's just a polynomial, so I can take the derivative of that easily. But the second one, I have to use the chain rule here. So what I would do is I'd still use g of x, but I would say, oh, I can't just, if this was the sine of x, then that would be easier. I'd just say it's a cosine of x, but because it's the sine of x cubed, I have to use the chain rule. So what you would do is you'd say, okay, g of u equals the sine of u, and u of x equals x cubed. Again, if I plug this into there, I get back. And so you take the derivative of each one of those, this with respect to u. So the derivative of the sine of u is the cosine of u. U prime of x is going to be 3x squared. It's a polynomial. So notice I'm doing this separately. It's taking a little bit longer. So then I use the chain rule, which says I take g prime of u times u prime of x, and g prime of u is the cosine of u times u prime of x, which is 3x squared. But that needs to be in terms of x, so I'll plug u back in. So I get the cosine of x cubed times 3x squared. And the final simplification is I'd move the constant to the front, then the squared term, and then finally that. And I go ahead and put a parenthesis to make sure there was no confusion that this is the cosine of the quantity x cubed. And the key thing to remember is you can never change the argument of this trig function when you do derivatives. So, somebody might be tempted, well, is this equal to x squared times the cosine of 3x cubed or something like that? And that's completely false. This never can change. So you can see I have sine of x cubed, I have the cosine of x cubed. The argument in the trig function can never be influenced by what's outside. You can change the trig function when we take the derivative, but what's inside can never change. The only way you could change things like that is if you use trig identities, and we're not going to use those, so don't do that. Another thing, too, is, there's these cases of the sine of 5x. So let's say that's f of x. So if you take the derivative of that, you could use the chain rule. And what you would do is you would say f of u is the sine of u, and u of x equals 5x. And you do f prime of u is cosine of u. U prime of x is 5. So using the chain rule, f prime of x would be 5 times the cosine of u, but u is 5x. So you get 5 cosine of 5x. We do this enough that you really shouldn't have to go through this long procedure. If you have a trig function, you take the derivative of whatever the trig function is, keep the argument the same, and multiply by whatever the derivative is of what's inside here. So you get 5, which is the derivative of 5x is 5. Take the derivative of the trig function. So let's say f of x is equal to the cosine of negative 7x. F prime of x, take the coefficient, take the derivative of what's in here, which is negative 7. Take the derivative of the argument, which is going to be negative the sine. Derivative of the cosine is negative sine. And you leave the argument untouched. In this case, you could clean it up a little bit. Negative 7 times negative 1 is positive 7, so f prime of x. So let's say I have the secant of 10x. That's my f of x. So what's f prime of x? Okay. The coefficient inside, put out front. The derivative of the secant is going to be the secant tangent, and the argument stays the same. So let's say f of x equals the tangent of 3x. The derivative is going to be the constant 3. The derivative of the tangent is secant squared. You leave the argument the same. Hopefully you leave the argument the same. If you change the argument, I'm really going to slam you. So don't ever change that. You might think, some people may say, it's going to be equal to the tangent of 3. You'll take the derivative of what you have in here, but the argument never changes. And then in this case, it wouldn't make any sense anyway, because the tangent of 3 is a constant. So it's just, okay. One last example. Let's say you had the cosine of 4x squared. Again, you could, in this case, you might want to write it out, but really, again, what you're going to do is what we've been doing here is we've been taking the derivative of the argument. Derivative of 5x is 5. The derivative of negative 7x is negative 7. The derivative of 10x is 10. The derivative of 3x is 3. The derivative of 4x squared is going to be 8x. So that's the derivative. You stick the derivative of the argument out front. You do the derivative of the cosine, which is negative the sine, and you leave the argument the same. And then in this case, we could bring the negative sign out and finally write it as such. Okay, I think I've harped enough on that. So the other two topics, besides just taking derivatives, simple derivatives, and is the implicit differentiation. So we did a whole sheet of that. The key thing is here that, how do you handle the derivatives like, well, let me just put an example up here. So let's say we have 8x to the fourth y squared plus 2x to the fifth minus 12 is equal to 7xy cubed. So that's the implicit equation. So the key things are people mess up are these products. There's a product. There's a product. So circle the product so you don't mess them up. What people do, this is where they mess up, is they'll take the derivative of both parts. So they'll take the derivative of that and they'll say it's 4x cubed times 2y prime. But when you have a product of two terms, you're going to end up with not just one term at the end, you're going to end up with two terms. And they're going to be simple like this, so you shouldn't have to write out the product rule. You should just think of what the product rule is. So if we take 8, we'll factor out the 8, and we'll take the derivative of this product with respect to x. So you take the derivative of the first term, which is the x term, 4x cubed, and you multiply by the second term. But you can't stop there. Then you have to take the first term times the derivative of the second. But because the second term involves y, instead of just being 2y, it's going to be 2y times y prime. Then you close the parentheses so you can remember to multiply everything by 8. The second term is only a function of x, so that one's a piece of cake. So you take 5 times 2 is 10, reduce the exponent by 1. The derivative of a constant is 0. And then we have another product, so we're going to factor out the 7. And then we do the same thing. We're going to take the derivative of the first term with respect to x times the second term plus the first term times the derivative of the second term. But because the second term is y, we have to include a y prime on there. So make sure you know how to do these things. If you don't, ask me. Ask somebody for some help. Okay, now once you do that, you multiply everything out so you can get all the terms individually instead of having these parentheses. So 8, actually we'll go ahead and multiply out. So 8 times 2, 16. 8 times 2 is 16 here. 8 times 4 is 32. Okay, then we've got x squared y prime plus 10x to the fourth is equal to 7y cubed plus 7 3 is 21, x, y squared, y prime. So once you've multiplied everything out, get rid of the parentheses, then you're going to take the terms that involve y prime, and you're going to put those on the left-hand side of the equation. And put everything else on the other side. So we still have 5 terms. Now we have 2 on the left and 3 on the right. The 2 on the left involve y prime, so you factor out y prime. And the right-hand side stays the same. And then you divide by the term in the parentheses. And typically you don't have to do anything to try to simplify things here. So you just leave it in this function as a rational function. I don't know what that is. Let's get rid of that. Okay, so that's how the implicit differentiation works. One thing I did forget to tell you is, and I'm not going to do it, but find the equation for a tangent line, so you can look at your equations. Equation of the tangent line. So I give you f of x, so that's given. You take f prime of x. So I'll give you f of x and some x1 and y1. So what I'm asking for is the slope of the tangent line at x1. So you take the derivative of the function, then you evaluate the function at x1. So you get a number. That's your slope. Then use the point slope formula in your equation. So you plug in x1, y1 in the slope, and then you solve for y. So make sure you know how to do those. And the final one is just related rates. So we did quite a few of those in class, and hopefully you understand it. I'm just going to give you the general procedure, and you can look at the homework to understand it hopefully better. But first is you need, you have to be given something. You're given some dimensions, like x and y. Or you might be given x, but not y. You might have to calculate it. You also are probably given some rate of change of that variable with respect to time. Then you have some other variable. So there's going to be some geometry, some geometric relationship. One that's commonly seen is the Pythagorean theorem. It's not the only one, but you may end up with the Pythagorean theorem relating the x's and y's. Or, the other examples we had were the law of cosines. We had Pythagorean theorem. We had volumes of circles and cones and rectangles. What else do we have? We had, what was that thing we were doing? The second problem, the third and fourth problem of the handout. It was, I can't remember. Let me look in my stuff you guys handed in to me today, because it was in there. Oh, it was the similar triangles. So, those are the kinds of things that you just have to look at the problem to decide which one applies. So we've got law. These are just things that we have used. Law of cosines. We used the definition of trig functions. That was like the 5th problem on our handout. We had similar triangles. we had the Pythagorean theorem. Even though we didn't have a lot of those on the handout, we did have a lot of those in the homework. Hint, hint, hint. Okay, so Pythagorean theorem. And what was the other thing we did? Oh, volumes and areas. Volumes, areas. So those are the kinds of geometric relationships that related the variables in the problem. So you have the geometry. Then what you do is you take the derivative with respect to time of the geometric relationship. So because both of these, all these are geometry, and this is time, you have to use implicit differentiation on all the terms that are in here. So for example, this one, you get 2x dx dt plus 2y dy dt is equal to 0. And then, if you look at this particular example, if I give you dx dt and I give you x, and I want to find out what dy dt is, the only thing you still have to find is y. And then you'll only have one unknown. So you can use this geometric relationship here, or you can use one of these other things up here to find the other variable, not the derivative of the variable, but the other variable value at that particular point in time. And then you can algebraically solve for it. So you solve, in this case, you'd solve for the one they're asking for, dy dt, and then you plug the numbers in. And you just got to be careful about signs. Whether something is getting shorter or longer. So, in this case, we have, sometimes the hypotenuse is constant. That was the ladder problem. We had the airplanes coming in, so you had an airplane going this way and an airplane going that way. In this case, you're actually given both of these, the rate of change of both of these, and the distance was what was changing. So if this is the ladder. For the ladder, this hypotenuse is constant, whereas in the plane case, we actually had x squared plus y squared equals s squared. And so when we took the derivative of this, we would get 2x dx dt plus 2y dy dt is equal to 2s ds dt. And that's fine. The thing is, if you're calculating ds dt, you need to know both of these, which would be the speeds of the airplanes. Whereas in the ladder problem, this part is a constant, so it's a little simpler. So there is a related rates problem on the test. And again, you're given some information about the geometry. You'll also have to be given the rate of change of one part of the geometry with respect to time. Use one of these relationships. This may not be an exhaustive list, but it covers most of them. So you have the geometric relationship, which relates the variables, the length variables, but doesn't involve time. So you take the derivative with respect to time. Then it becomes a rate problem. And at that point, you try to make sure you know everything. And if you don't know everything, you may have to go back to this geometric relationship to solve for the one that you don't know. So then you solve for what you're asked in the problem, plug in the numbers, be careful of the signs. So yeah, I was talking about that. So let's say these airplanes, here dy dt is negative, here dy dt is negative. If you had the planes flying away from each other like this, so they're going this way and that way, dy dt would be positive and dy would be positive. If one's going this way and one's going that way, then one's going to be positive and one's negative. For the ladder, if the ladder's going like this, dx dt is positive, And as a consequence, dy dt has to be negative, because if this thing slides out, it's going to go down. If you go the other way, say I'm pulling the ladder up, then dy dt is positive and dx dt is negative. So they're always opposite each other on a ladder. For airplanes, it all depends on which direction they're going. We also had the dot problem, which is still a Pythagorean theorem problem. In that case, the distance, the vertical distance was the thing that stayed the same, the distance from the water to the dock. Okay, yeah, so it took me 17 minutes, so I'm going to give you an hour and 15 minutes to work on this, and hopefully you'll all get A's.